So now let's talk a little bit about hydro capacity. Annual weather and precipitation cycles are really going to affect hydropower production. The hydroelectric resource potential is going to depend on a combination of rainwater that drains directly into waterways and to a large level the amount of accumulated snowpack in mountainous regions that will eventually melt and become runoff. For this reason, hydroelectric generating capacity may be derated in long-term forecasts, meaning that hydroelectricity generation capacity, despite the fact of the size of the turbines, we might have to apply discount factors up to it in the same fashion that we'll see we would derate wind generation capacity resources. Because hydropower is comparatively inexpensive, fossil-fired generation and even wind generation is often curtailed during times when hydro generation is high. Here what we see is we've got hydropower and other renewable electricity generation plotted from 1990 in the United States until 2010. The units are in millions of megawatt hours. You can see hydropower dominates the renewable energy portfolio of the United States in these graphs every year. For example, in 2010 we had 250 million, about 250 million megawatts of hydroelectricity, and we're kind of about 175 million megawatts of other renewables. Notice there's a huge fluctuation in the amount of hydropower that's actually being produced year after year, and that's not because plants went offline or new plants were built or anything like that. That fluctuation is largely due to the water resources that were available for it. For example, this past year, this chart only goes up to 2010, but in 2014, the 2013 snowpack in the Sierras was extremely small. So if you extend this graph out to this current year, you're going to see a much smaller hydropower output in the Pacific Northwest region in particular. While national hydropower output's often dominated by hydroelectricity generating capability in the Pacific Northwest, that's where most of the dams are, it is possible for other regions of the country to have opposite hydropower trends in the same year. And so that's what we're showing here. We're looking at annual hydropower generation by region, and we see deviation from averages. So what we see is that 0% would be, that's the average value, and then each year, did we produce more or less electricity from hydropower than would have been average. So in 1990, we see that in the Pacific Northwest, we produced a little bit less than 10% more electricity than average, and we produced about 15% more electricity than average in the Southeast. So similar trends, we produced more hydropower, meaning that there was a more available water resource. That trend continued throughout the 90s, but here we get to, I don't know, this might be like 1992. We look at 1992, and the Pacific Northwest actually saw a derating of their facilities. They produced about 15% less hydropower because of low water levels. Where in the Southeast, we still produced about 12% more electricity. And you can kind of investigate these trends over the course of time here. The point being that even if you have a hydropower facility, you have to have the water to be able to run that facility. The water has to fall. It has to fall as snow. It has to fall as rain. And it has to stock our aquifers, our rivers, our lakes, our streams, and things like that. So, if we look at this, in 2009, the southeastern United States had record high reservoir levels and high levels of hydropower generation, while in the Pacific Northwest, they received below normal precipitation, and as a result, they had extremely reduced levels of hydropower generation. These hydroelectric power generation resources are spread really unevenly across North America. Some regions, like the Pacific Northwest, generate a significant amount of their electricity from hydro, while others only have limited hydro resources available to them. On average, though, about 6 to 9% of U.S. electricity generation is produced by hydropower per year, depending on the water availability. The size of the hydroelectric power generation, the size of the dams also varies. In fact, the largest plant in the U.S. is the hydroelectric plant in Grand Coulee Dam in Washington State. It's got a capacity of a little over 7,000 megawatts. And although they're not considered either in Pacific Northwest or Southeast, Alaska and Hawaii both have a small amount of hydroelectricity. So let's look more specifically at that hydro inventory. or the distribution of hydroelectric plants across North America, or more specifically, I guess, across the United States and Canada. The inventory of U.S. hydroelectric generating plants consists mainly of three types of plants. We've got conventional hydroelectric generators that are incorporated into dammed reservoirs, and these supply us with kind of a relatively stable supply of water. We've got other conventional run-of-the-river plants, meaning that they have no reservoir and their generating output is subject to change in the flow of water in the river. And then we've got these pump storage plants that we talked about earlier that can function as energy storage, given that they have the ability to reverse their turbines. A large portion of the power imported to the United States from Canada is also generated from hydro. In the east, hydropower from the Quebec area up in here is also generated from hydro, and it's particularly important in serving the northeastern United States, New York, Boston, Philadelphia. In the Midwest, a transmission line delivers hydropower from Manitoba to the U.S. with minimal contact with the rest of the Canadian grid all the way. So we get a lot of hydropower delivered to, the Midwest area from Manitoba. In the Pacific Northwest, the Columbia and Snake River basins are geological and topological units with abundant water availability and river flows on both sides of the border. And the preponderance of hydroelectric capacity on the U.S. side of the border here tends to limit any sort of benefits of trade between Canada and the United States in those regions. Unlike other traditional electrical energy resources, hydropower facility construction is extremely limited by geographical considerations. Currently, the United States has a large inventory of non-power producing dams across the country. Approximately 80,000 plus such facilities exist, primarily used for services such as regulating water supply and controlling inland navigation. Of these, it is estimated that about 50,000 sites are suitable to be upgraded to hydroelectric facilities with a technical potential of about 12 gigawatts of hydro capacity. Of these 50,000 sites, the 100th largest capacity facilities combined would produce 8 gigawatts of that power. So estimates have also been made of new stream hydro potential in the United States, which when federally protected lands are excluded, represents an additional 65 gigawatts of power capacity. So if we looked at all the existing dams in the United States that currently don't provide hydro, but could be upgraded to provide hydro, we could get about another 12 gigawatts. And then if we exploited all the hydro capacity in the existing rivers in the United States, we could get another 65 gigawatts. So there is about 77 gigawatts of unexploited power hydro capacity in the United States right now. You'll notice preponderance of hydropower in the Pacific Northwest in particular. That's the Bonneville Power Administration. And then you also see that there is a preponderance in the Cumberland Plateau, and that's the Tennessee Valley Authority. If you're going to work in the hydropower industry, those are kind of the big dogs, TVA and BPA. Although considered a renewable energy resource, hydroelectricity still does have associated environmental impacts. Hydropower's air emissions are almost negligible because no fuels are burned. However, if a large amount of vegetation is growing along the riverbed when a dam is built, it can decay in the lake that's created by the dam, causing buildup and release of methane, which is a greenhouse gas. So there are some people who consider that hydroelectric dams do produce greenhouse gas due to decaying plant matter in the dams, although it's a fraction of a fraction. Hydropower often requires the use of dams, which kind of seems obvious, which can greatly affect the flow of rivers. It alters ecosystems and affects the wildlife and people who depend on the waters that were previously available to them. Often water at the bottom of the lake created by a dam is inhospitable to fish because it's cold and oxygen poor compared with the water at the top. When this colder oxygen-poor water is released into the river, it can kill fish living downstream that are accustomed to warmer, oxygen-rich waters. In addition, some dams withhold water and then release it all at once, causing the river downstream to suddenly flood. This action can disrupt plant and wildlife habitats and affect drinking water supplies. Hydroelectric plants release water back into rivers after it passes through turbines. This water is not polluted by the processes of creating electricity, but the construction of the hydropower plants can alter sizable portions of land when dams are constructed and lakes are created, flooding land that may have once served as a wildlife habitat, farmland, or maybe scenic area. Hydroelectric dams can cause erosion along the riverbed upstream and downstream, which can further disturb wildlife ecosystems and fish populations. So There is a lot of concern in particular about fish populations, as hydroelectric power plants affect various fish populations in different ways. I think most notably certain salmon populations in the Pacific Northwest up here, they depend on rivers for their life cycles. These populations have been dramatically reduced by the networks of large dams in the Columbia River Basin. In particular, we're referring to salmon. When young salmon travel downstream towards the ocean, they may be killed by the turbine blades at the hydro plants, and then famously when the adult salmon attempt to swim upstream to reproduce, they may not be able to get past the dams. Engineers creatively have created special side channels or fish channels or structures to help the fish continue upstream. You may have seen videos of these salmon jumping up these kind of hydroelectric paths. Recently I saw a YouTube video where somebody has, like if you go to the bank and they've got those funnels that suck your check into the, using air pressure, and it sucks your check into the teller, and they fill out the check and then they send it back to you. Well, now some of these dams have fish funnels, and it uses air pressure to suck the fish in. I think they call them salmon cannons. So if you're interested in those, Google salmon cannons. You'll get a funny video to watch. The point being is that although hydroelectricity is considered a renewable energy resource, and it is the most vast renewable energy resource in the United States, it does have some environmental impact that we do have to be aware of when we're considering creation of a new hydroelectric facility. So let's take a look now at how much power and energy we can actually extract from stored water. So the energy stored in a water held at elevation is, as we said earlier, in the form of potential energy. If a mass of m kilograms of water is raised to the height of h meters, the stored potential energy is just given by the potential energy formula. Potential energy is equal to mass times gravity times height. And in this equation, mass and height are your variables. G is the acceleration due to gravity, and hopefully you know this by heart by now, but if you don't, it is 9.81 meters per second squared, right? Meters per second squared being the units of acceleration. In the case of a hydroelectric plant, m here is the mass of water stored in the dam, and h is the head height, the difference between the penstock and the top of the dam, or the top of the water stored in the dam. The power supplied in watts is just the rate at which this energy is delivered, i.e. the joules per second. So that power calculation therefore depends on the mass flow rate of the following water, or think of it another way, the kilograms of water that flow per second. And so if we were going to write the power equation, it would be power delivered is equal to the flow rate, Q, times the density of water, rho, or whatever the flowing material is, then times GH, right? So remember, this is just energy per unit time, and so the units for these guys is going to be meters cubed per second. Right, flow rate, it's a volumetric volume flow rate. We then multiply by density, right? So density is just how much does it weigh per unit volume, kilograms per meter cubed. And then again, we have our meters per second squared times height, right? Oh, times meters, not times height, times meters. So again, in this equation, Q is the flow rate, meters cubed per second. Rho, the Greek letter rho, is the density, kilograms per meter cubed. When we evaluate real systems, we must also take account energy losses. In any real hydro plant, the kinetic energy of the water as it's moving, although all the potential energy does get converted into kinetic energy, the kinetic energy of the water will be reduced due to frictional drag and turbulence. This loss results in effective head height that is less than the actual head. So we can fully convert potential energy into kinetic energy, but then once that water starts moving, there's turbulence, there's drag, it reduces the available amount of kinetic energy to us, and how we account for that is we reduce H, and we give it what's called an effective head height. Effective head heights are going to range from 75 to 95% of actual head heights in most hydro plants. And although the hydroturbine generator is one of the most efficient electrical generation technologies, it is still less than 100% efficient, and output power calculations have to incorporate this efficiency loss. So what we need to do is we need to modify this equation right here, and we need to say that it actually is equal to the efficiency of the electromechanical generator, as we talked about in the first two parts of this lecture series. We then multiply by the rest of this equation, Q rho G. And then instead of multiplying by H, which is the head height, we need to multiply by the effective head height, H effective. And so this here gives us the actual formula for amount of power that is delivered to us by a hydroelectric facility, efficiency of the electromechanical generator, flow rate, density of the flowing liquid, acceleration constant, and then the effective head height. Right? So what we want to do next is we want to utilize those formulas in performing a calculation in available power from a hydro plant. So we've got two hydro plants. We've got one that's a mountain stream with an effective head of 25 meters and a flow rate of 600 liters per minute, and it has a 83% efficient turbine. And then we've got one, instead of a mountain stream, we're going to compare it with Niagara Falls. Niagara Falls has an effective head height of 100 meters and a flow rate of 6,000 cubic meters per second. It also has an 83% turbine efficiency, so they're using the same efficiency turbine in these two systems. So we want to calculate the power that's available under these two different conditions. Okay, so to solve this, the first thing we need to do is write the power equation. P is equal to efficiency times the flow rate in cubic meters per second times the density in kilograms per cubic meter times the gravitational acceleration constant, meters per second squared, times the effective height, h. So now we just need to apply this to both situations. In the first situation, we had an 83% efficient generator, 0.83. We had a flow rate of, unfortunately, 600 liters per minute, which isn't in the appropriate unit, so we need to convert that over. So that's going to be times 600 liters per min. There are 0.001 cubic meters per liter. And then there are 60 seconds. 1 minute is 60 seconds. Multiply all that out. So that gives us our flow rate in volumetric meters per second. We need to now multiply by the density of water at 1 atmosphere at standard temperature, at room temperature, is 1,000 kilograms per meter cubed. That value is going to change based on altitude and also temperature, so more sophisticated analysis would take fluctuations in water density into account. Don't worry about it for this class, but just be aware that that is a assumption or a simplification. We now need to multiply this by 9.81 meters per second squared. Again, a simplification, 9.81 meters per second squared is only true at sea level. It is higher at lower elevations. It's lower at higher elevations. Most dams are at higher elevations, so you typically have to derate this gravitational acceleration constant. But then we were given the effective height. This tiny dam was 25 meters. And that gives us 2,035.6 watts. So that's for the small stream, and then for Niagara Falls, it was 0.83. The major change here first is that the flow rate is 6,000 cubic meters. Much bigger flow rate per second. And then density of water stays the same, 1,000 kilograms per meter cubed times 9.81 meters per second squared I then need to multiply it by the height. For this last one, it was 100 meters, much taller dam. And we get 4.89 gigawatts of available electric power, considering both the efficiency and the effective head of the hydroelectric dam.